go back over just some like conceptual things, right, Wade? All right, so being able to look at the particle diagram of solids, liquids, and gases, knowing that solids are tightly packed together, liquids, you draw them with a little bit of space in between, and gases take up the space of their container. They got lots of empty space. Remember, mostly empty space. All right, as you see, the solid is in its own shape. The liquid is where we begin to take the shape of the container. All right, and so then we talked about the properties in this lovely table. All right, and so we talked about the motion of solid, liquid, gas going from a solid vibrating in place, no matter how cold it is always vibrating. Your desk is vibrating, the floor is vibrating, your pencil, everything is vibrating. Oftentimes I see people say the molecules in solid are staying still. They never stay still. You would have to be at 0 degrees Kelvin or absolute zero in order to stay still. Because remember, temperature is a measure of motion. So as long as it has a temperature, it has a measure of kinetic energy. Then as we heat up into a liquid, there's short distances. They have some fluid motion. They get to move randomly. And then gases become very random, rapid, straight line movement. Remember I said, like, think of the screensaver that goes on the TV, like corner to corner, straight lines. Little bumps into something. Spacing, solid, tightly touching like you see in the particle diagram, and then they spread out in the liquid, and then mostly empty space in a gas. Our intermolecular forces refer to the force between these particles. So when they're in a solid, that force is really strong that's holding them together. All right? And then as it starts to weaken, these particles get to move away, right? So we overcome that force by the energy that those particles gain. As they gain energy and they start moving faster, they're able to overcome the force that they feel towards each other, and they start to spread out. And then by the time they turn into a gas, they're way spread out, and they're so far spread out that you don't even feel a pull between them anymore, right? So remember I compared it to magnets, and you take the two ends of the magnet, and when they're side by side, there's a really strong force holding them together. But as you back away, it gets weaker and weaker, right? And then we talked about the volume and the shape. Your desk will never be in another shape or take up more or less space than it does right now, unless you were to like actually alter it, right? In just the normal sense, it will never be in a different shape and never take up more space. But then in a liquid, our volume stays the same, right? A 2 liter of soda will always be a 2 liter of soda, no matter like what I pour it in, the shape of the container. And then gases, they're going to expand and take the shape of the container. If Wesley's lunch didn't set right, you're going to find out back there. Oh. Because the gas spreads through the container. And then the indefinite shape. So it's going to take the shape of whatever container it's in. And then density, that was just your common measurements. You don't need to be as familiar with those. Right? But you will never forget gases now. All right. And then we looked at particles. All right. And this was part of looking at water's unique design. If you look on test day, it'll tell you need to be able to know about water's unique design and why it's important. Why does it sustain life? All right, and so if we look at solid argon, solid neon, and solid oxygen, how do they look different than solid water? Notice water, that's still selected as solid. What's different?
It's the charged particles, right?
Yes, it's due to the charged particles. What did you say?
Expanded.
It's expanded, yes. So all of these get to tightly pack together because they're intermolecular forces, but water has hydrogen bonding in it. And you'll see this to some extent in all molecules with hydrogen bonding, but water is kind of the most dramatic where you'll see that. And so as you notice, all the whites are pointing to the reds. And that's because your hydrogens, as we'll talk more next unit about, are partially positive and oxygen's partially negative. All right, so imagine them as magnets. Two oxygens don't want to get near each other because they have the same charge. And so then they end up spreading out, and that is why you see ice. It expands when the water freezes, and B, that's why it floats, because now it's got all these little air pockets in between, if you want to say, and then it's going to float on the top surface because the density is less. All right, so that allows when the oceans and rivers freeze, ice doesn't sink to the bottom and kill all the fishies and the vegetation. Instead, it floats to the top. All right? Then we talked about pressure before we looked at our phase diagrams. And so pressure is the force per unit. And remember, it is caused by molecules colliding. Collisions equals pressure. More collisions equals more pressure. And so we talked about atmospheric pressure. When you're at sea level, it's 1 atm. Above sea level, you've got less atmosphere weighing down on you, so it's lower. And below sea level, you've got a lot of atmosphere weighing down on you, and it's going to be higher. Vapor pressure, we talked about if you were to boil a pot of tea on the stove, or if you boil a pot of water and you have a lid on it and the lid starts to rumble. That's because as it starts to evaporate, you get more molecules and more vapors, and those particles start to collide into the walls of the container and the surface of what's still liquid, and it builds up pressure. All right, so more collisions, more pressure. And then partial pressure, that's saying if I have the total pressure in this room, and I know the value to be, let's say, 0.85 atms. All right, and I said, well, there's oxygen gas in here, there's helium gas, and let's say neon gas. And I wanted to know what was the pressure of oxygen if helium is hydrogen is 0.15 and neon is 0.65. This is totally unrealistic, but so then you get a total of 80. So then how do I get to 0.85? This would have to be 0.5. So partial pressure just says that the total pressure is made up by a bunch of different gases having their own individual pressure. So that's how you get, like at 1 atm, it's not just one gas that's giving us atmospheric pressure. There's all the gases around us giving atmospheric pressure. All right, are we good? So then after we talked about pressure, we looked at its effect on the 3 phases of matter. So you need to be able to identify the different regions on this. So they go in the order that most of you are used to saying it: solid, liquid, gas. So here's your solid at lower temperatures, liquid, and then gas here at the higher temperatures. And so we see that as I were to pass from a solid to a liquid, I would be doing what? Melting. Pass from a liquid to a gas, I am evaporating. And then I can go back and forth between solid and gas as well. And remember, sublimation starts with a solid, starts with S, and then deposition is going back the other way. Be able to identify those changes and what's happening as you go from lower temperatures to higher temperatures, or lower pressures to higher pressures. All right, and we talked about your triple point. Triple means 3, so that's where all 3 of them come together. And so we looked at that video of cyclohexane, and it was boiling and freezing and liquid all at the same time. Then we looked at the unique design of water in a phase diagram. Notice the one up here. These are most all of your other substances. Points to the right, up and to the right, but then water is up and to the left. What does this allow for? This tells us that water is still going to be a liquid at higher pressures, and with the same temperature is a solid at lower pressures. All right, so this affects, like when you see on the side of a baking box and it says at higher altitudes, cook at this temperature, right? Because the atmospheric pressure has dropped, and therefore you need to cook it at higher temperatures in order for the liquid to still do the same thing. All right, this is also why if we look at water and ice on a grander scale on the oceans, that's why the surface is going to freeze before the underneath, right? Because lower pressure areas become a solid before higher pressure areas. So I'm looking at the unique design of water, and I talked about how God points this out in Job and is like, did I not design this way? And so in Job, he says, does the rain have a father who fathers the drops of dew, from whose womb comes the ice, who gives birth to the frost from the heavens? And when the waters become hard as snow and the stone, and the surface of the deep is frozen. And so of all the things that he could point out, he points out that unique design of water. Like, I freeze the surface of the oceans, right? Knowing, and now we can look at these and say, wow, water behaves so much differently than everything else, right? We look back here and we see how it expands, and that allows it to float to the surface. And then we see how it freezes at lower pressures, unlike all the other substances. So again, allows it to maintain that frozen ice on the surface, right? If it didn't do that, then we would not have any ocean life, all right? And so life in the ocean and things that depend on life in the ocean would cease to exist. So very unique to see how he points this out when we look at it and say, oh, wow, this is like unique. And he points that out of all things, all right? Then we moved forward from that, and we talked about standard temperature and pressure. These are standards. So standard temperature is 0 degrees Celsius. How do I get to Kelvin? Add 273. And then standard pressures. These are your base units that you use to do pressure conversions. All right, so let's take a look at, and you need to know these. You need to memorize them. You need to know your values. All right? So let's look at an example of a pressure conversion. 12 psi's to torrs. So write down what you're given, 12 psi's, and I want to go to torrs. Well, what is the base for torr? 760, yes. All right, that's where I'm going to. And then whatever goes up must come down. So psi is here. Whatever goes up must come down. And therefore, what is the base for psi? 14.7. All right, so next slide, working through this, and this is in your notes in case you need to go back over it. Multiply across and divide. So 12 times 760, 9,120 divided by 14.7. And so 12 psi's is equal to 620.4 torrs. All right, questions? And then we did our Celsius to Kelvin conversions. What do I do?
Add 273.
Add 273, all right? So we're getting to the part that you all should be most familiar with. And then this one, I noticed a lot of you are still working on understanding this, all right? This is not something that you want to memorize. You want to actually know it and understand it, all right? Think about it, be able to explain it. You will have an essay question that asks you to explain how these three factors impact pressure. All right, we know pressure is a direct result of collisions. So when I increase temperature, what am I actually doing?
Increasing speed.
Increasing speed, all right? Because temperature is really a measure of kinetic energy. Kinetic energy is motion. So when I increase temperature, I increase speed. Good job. All right, and then when those particles start moving faster, it results in more collisions. If you forget, remember I used the example of a car going down the road. 25 versus 95. Number of collisions are going to increase the faster you go. And those collisions directly relate to pressure. And then we talked about moles. Moles is what?
How many molecules?
Yes, how many molecules there are. So if I increase the number of moles, what I'm really doing is I'm putting more particles into my container. And so same amount of space, but more stuff has to fit in there. Therefore, there's going to be more collisions. And as there's more collisions, the pressure again starts to build. And then last one was our volume. And so what is volume? Volume is actually a measure of how much space is available. So when I increase the volume, I give my particles more space, and therefore less collisions, less pressure. All right? That right there is what you need to be able to explain on your test. We good? And so then we talked about the mathematical relationships between those variables. I saw a lot of questions about this on your lab. What is direct? What is inverse? All right, so inverse are those variables that are on the same side of the equation. So pressure and volume would be inverse to each other, and moles and temperature would be inverse to each other. Because in order to maintain that balance or that equal sign, if I increase pressure, I have to drop volume. All right. And so the graph of the inverse of an inverse relationship will be a straight line. The graph you all drew was that negative curve. All right. So be able to recognize that negative curve. This is the inverse of the inverse. You all just did the inverse. So that was that negative curve. And then direct are those variables on opposite sides. So therefore, as I increase pressure, something on the right needs to increase in order to maintain the balance. And so then you get your positive slope. I know most of you are still familiar with this, but we're getting to some parts that I want you all to look at. Ideal gas law. So remember, this is the one that has our R value. And R is dependent on the unit for pressure. A lot of questions on this. So ATMs, we're going to use 0.0821. KPAs was 8.314. And then if your pressure is given or asked for an MMHG, 62.4. So ideal gas law, one thing you can see to look at, remember that R value tells you my volume must be in liters, yes, and then it determines the pressure because you need to match it with the right one, and temperature must be in Kelvin. All right? And so you know you're using the ideal gas law because A, you're going to see moles. Probably mention moles. It's got to be ideal gas law. Or B, it has all the variables only once. So let's look at an example of that. This is one that we weren't directly given moles, and so let's review over it. When you identify your variables, what is the pressure? So pressure is what I'm looking for in ATMs, exerted by 18 grams of H2 in a 4.3 liter balloon at 27 degrees Celsius. And so I determined my R value because 0.0821 is the one that matches ATMs, right? And so when I'm reviewing over these variables, I notice, wait, this says grams, but I need what? Moles. This says Celsius, but I need Kelvin. All right? So how do we get grams to moles? Convert it how?
Do the little flowchart.
Yes, so grams to moles, I need you to divide by the molar mass. So I'm given 1.8. I want to get to moles. Whatever goes up must come down. Where did I get 2 from? Well, it's 1.8 grams of H2. Hydrogen weighs 1, and there's 2 of them, so 2 grams.
So we'll have our
Pure egg table.
Yeah.
Yes.
Nice Russian.
Nope. Wait a minute. All right, and so then you get 0.9 moles for your N, and temperature is 300. And then we would plug it in as usual. That is the part that I wanted you all to see, though, that I noticed a lot of people have forgotten about. Right?
We'll have to memorize the R's too, right? Or will that be?
Yes, you have to know your R's. All right, and so then you plug it in and solve for P. Once you simplify, please do not get rid of your variables. I see a lot of you get rid of this once you simplify. Do not get rid of it because then you end up multiplying and dividing the wrong sides. And solve for your answer. So, modern vacuum technologies techniques make it possible to reach a pressure of 1 times 10 to the negative 10 mmHgs in a lab system. So let's write down our pressure. Hang in there. I know some of you all are ready to start working. 1E negative 10. And Isaac, that E is just how we plug in our scientific notation into the calculator. Times 10 gets replaced with E. All right? It helps your calculator know what's going on and know that it's scientific notation instead of doing it the wrong way. Otherwise, your calculator follows PEMDAS. So what volume? I'm looking for volume in milliliters. So I know that my V is the question mark, and I want it in milliliters. Would a 1.143 times 10 to the negative 6 molecules of gas occupy? So I'm given molecules, 1.143 E6. And just write this down to the side. Molecules. All right? At this pressure, at standard temperature, which we know is what? 0 degrees Celsius or 273 Kelvin. Temperature equals 273. All right? PVT. Everything's mentioned once. So what gas law does this have to be? It's only mentioned once.
Oil.
No, it's
No, it's
it's the first one.
The first one, PV equals
NRT.
nRT. Yes, good job. So we need an R value. Remember, R is based on our unit of pressure. Well, mmHg is what?
760.
101.325.
Nope. Those are the bases. You see a lot of people getting R and base confused.
Something 8.
62.4 liter mmHg's per molar Kelvin. Y'all are getting R's and standards and bases confused. All right, so if I look here, I've got my pressure, I want to find volume, but I don't have anything to plug into N. Well, what can I do? Molecules to moles. Remember Pam to moles, moles to grams?
Yeah.
So 1 mole is my base. Whatever goes up must come down. Well, what's the base for molecules?
6.02
E23, yes. All right, somebody have a calculator?
Yeah.
You need an E button, so
Yeah.
there you go. Okay. 1.143 E6 divided by 6.02 E23.
It's 2.38 E negative 18.
There you go. All right, and so that is your N value now that you have found the number of moles. And so we get to plug that in. PV equals nRT. So my pressure 1E negative 10 times V equals 2.38 E negative 18 times 62.4 times 273. How do we get V by itself?
Divide it.
Yes. 1E negative 10, which ends up V equals 4.05 E negative 4. Well, if we look up here, we know that because R is liter mmHg's, what is this? Liters, right? Volume is in liters. But it asks us for volume in what? Milliliters.
So what times by
So, all right, let's take it out of scientific notation. That's going to be the easiest way to see it. So this is negative 4. That means we're moving our decimal forward 1, 2, 3, 4 times. All right, so I have V equals 0.0000405. Same number. I just moved the decimal forward. Liters. How do I make that milliliters? Here's base.
multiply by 1,000.
Move it over 3 times, or yes, multiply by 1,000. So 1, 2, 3. And so my volume, 0.405 milliliters. That's what I wanted you to see, right? Because your answer is given to you in liters, but it's asking it from you in milliliters. All right?
That was all one ball.
That was all one problem.
Ouch.
So it is the same one as that example where y'all were like, oh my gosh, I already know how to do this. Why are we still doing this? Right? But that's why I did that, to give you like that base understanding. Yeah. And then lastly, combined gas law. You know you're using the combined gas law when you're given 2 sets of conditions. It doesn't even mention moles, right? We don't have an N in here anywhere. And you're given 2 sets. So I start with the pressure, I end with the pressure. This one, it only matters that temperature is in Kelvin. Volume, because there's no longer an R in this problem, volume does not matter, pressure does not matter, as long as they match. So both pressures need to be the same and both volumes need to be the same. So looking at an example here, I'm given pressure at 25 liters at 1 atm. If the pressure is changed to 1.5, what is that new volume? And so remember, you mark out that variable that you don't need. Make your life easier, mark it out. And PV equals PV, and you're solving for that missing variable. If you have a question, let me know, but most of you are good on this, so I'm just going through it. And you get your volume. What is this? What law is this? Other than combined gas law, what derivative of combined gas law is this?
Charles law.
Try again. Boils. Remember I said, look, it looks like boils. You can make a boy out of it. So you can't do that with Charles. So that's just one way to help you memorize that. PV equals PV is boils. And so remember, boils, pressure, and volume are inversely related. So that's where you see that negative curve. And then you have Charles's law, volume and temperature. And you see your positive relationship. What team was it that has a deflated ball? The Patriots?
Yeah.
Right? So this actually came into play when they were looking at what happened, because it was like, no, we actually pumped it up to the right pressure, the right volume that it should be at. But because we came here and the temperatures were lower, as the temperatures dropped, my ball deflated. Right? So this was actually pulled into play when they looked at that. So Charles' law, real life application into sports. All right? So, pretty cool fact.